Of all the celestial bodies traversing the vastness of space, none has captivated the human imagination quite like Mars. In ancient times, the red planet was revered as a god of war. Today, it serves as the quintessential backdrop for countless works of science fiction, novels, films, and more. Now that humanity has reached its surface, with robotic landers touching down and tirelessly exploring its terrain, Mars has ceased to be merely a figment of fantasy. It has become a tangible destination, one that may one day welcome human footsteps. Mars is the fourth planet from the Sun and the outermost of the so-called terrestrial planets, rocky worlds comparable in composition, if not size, to Earth. It orbits the Sun at an average distance of 200 million kilometers, placing it beyond Earth's orbit and never coming closer than about 60 million kilometers. The Martian climate is significantly colder than Earth's, with surface temperatures plunging as low as -60 degrees Celsius. Though modest in size, its diameter is less than half that of Earth. Mars can appear strikingly vivid in our night sky during its closest approaches. Its crimson glow resembles a baleful eye, a sight that surely inspired ancient civilizations to link it with war. Yet this red hue stems not from blood, but from rust. The planet's distinctive color arises from fine, rust-colored dust blanketing much of its surface, essentially a layer of iron oxide particles resembling red powder. This dust, rich in oxidized iron, imparts a reddish-brown tint to the landscape and is frequently lofted into the thin atmosphere by winds. Beneath this dusty veneer lies a surface largely composed of gray volcanic rock known as basalt, which, combined with other minerals, contributes to Mars' overall reddish appearance. Mars is easily visible from Earth, though discerning fine surface details remains challenging. Until the 1960s and 1970s, hopes persisted that Mars might harbor a temperate climate and even life, until spacecraft sent back images of a starkly dry, barren world. Martian geography is remarkably diverse. The northern hemisphere is dominated by flat plains, while the southern hemisphere is heavily cratered and rugged. Scientists believe that millions of years ago, Mars suffered a colossal impact from a celestial body hundreds of kilometers wide. This cataclysm created a vast, lava-filled basin near the planet's north pole. Topographic maps clearly show that the northern lowlands sit significantly lower than the southern highlands, by several kilometers in places, creating a noticeable slope from south to north. One of Mars's most prominent features is the Tharsis Bulge, a vast volcanic plateau that hosts 4 of the planet's largest volcanoes, including Olympus Mons, the tallest known volcano in the solar system. Though Mars lacks active tectonic plates today, evidence suggests they may have existed in the past. Tharsis likely formed over a mantle hotspot, a rising plume of hot material beneath the crust. As the crust slowly moved over this hotspot, magma repeatedly breached the surface, building not only Olympus Mons, but also 3 other massive, though slightly smaller, volcanoes. Yet perhaps Mars' most spectacular feature is Valles Marineris, a colossal canyon system discovered by NASA's Mariner 9 orbiter in the 1970s. Stretching 4,000 kilometers long, up to 200 kilometers wide, and plunging as deep as 7 kilometers, It dwarfs Earth's Grand Canyon by a factor of 10 in both length and width. Unlike the Grand Canyon, however, Valles Marineris was not carved by water. Instead, it likely formed as the Tharsis bulge rose, fracturing the crust along a line aligned with the bulge's diameter. Like Earth, Mars has polar ice caps, both composed primarily of water ice several kilometers thick. Seasonally, however, they become coated with a layer of dry ice, frozen carbon dioxide, ranging from 1 to 8 meters thick. Each winter, CO2 freezes out of the atmosphere onto the poles. In summer, sunlight sublimates it back into gas, triggering powerful winds that sweep across the landscape. Mars does possess an atmosphere, but it is extremely thin. Surface pressure is less than 1% of Earth's, and composed mostly of carbon dioxide. Each winter, nearly a third of the atmosphere freezes onto the poles. This tenuous air offers little protection from meteoroids and comets, leaving the surface heavily cratered and still vulnerable to impacts. NASA's Mars Reconnaissance Orbiter has orbited the planet long enough to capture images of fresh craters formed by recent collisions. Despite its thinness, the atmosphere actively shapes the surface. Seasonal winds fill craters with dust, and the sands, derived from weathered basalt, appear gray. These winds sculpt stunning dune fields, including parallel ripples on crater floors and crescent-shaped dunes. Orbiting spacecraft have also observed towering dust devils, similar to terrestrial tornadoes, which, as they disperse red dust over gray plains, create intricate, wrinkle-like patterns. Among recent discoveries are Martian snow avalanches. In spring, buried CO2 ice sublimates on steep slopes, triggering massive debris flows of rock and dust. Orbiting spacecraft have captured these avalanches in action, an extraordinary testament to Mars's dynamic geology. Mars has two tiny potato-shaped moons, Phobos and Deimos. Phobos measures about 25 kilometers across. Deimos is even smaller, at roughly 15 kilometers. Both resemble asteroids, leading to the hypothesis that Mars captured them from the nearby asteroid belt, though their exact origin remains uncertain. Phobos orbits just 6,000 kilometers above the surface, moving faster than Mars rotates. As a result, it rises in the west and sets in the east, a phenomenon visible from the surface. Mars' gravity is steadily pulling Phobos closer. In a few million years, it will descend low enough to either break apart in the atmosphere or crash into the planet, an event that would be spectacular to witness from a safe vantage point. From certain locations on Mars, both moons can be seen transiting the Sun. Rovers have captured stunning images of these events, a remarkable achievement in planetary exploration. This raises a natural question. If Mars has rocks, an atmosphere, weather, and volcanoes, does it have water? We know water ice exists at the poles, but what about elsewhere? Subsurface ice has been confirmed in mid-latitude regions, evidenced by bright patches around fresh impact craters, where collisions have exposed buried ice. However, there is no conclusive evidence of liquid water on the surface today. Some crater walls show dark, narrow streaks that appear to flow seasonally, possibly indicating briny water. But alternative explanations, such as dry granular flows, remain plausible. Yet Mars's past was dramatically different. Abundant evidence, dry river valleys, ancient lake beds, sedimentary layers, and water-dependent minerals, attests to a time when liquid water flowed freely. There are even signs that vast oceans once covered the northern lowlands. But this water vanished. Billions of years ago, Mars was warmer and its atmosphere denser. Then, for reasons still not fully understood, its molten core cooled, its global magnetic field collapsed, and the planet became exposed to the solar wind. Over eons, the atmosphere was stripped away, and with it, the water. This leads to the most profound question of all. If Mars once had air and water, could it have harbored life? Once dismissed as speculative, this question now drives major scientific investment. Rovers and orbiters are actively searching for signs of past or present life. Life on Earth emerged rapidly after our planet cooled, and since Mars is smaller, it cooled faster. It would be illogical not to wonder whether life might have arisen there even before it did on Earth. NASA's Curiosity rover has detected simple organic molecules in Martian rock, a finding that, while not proof of life, confirms that life's essential building blocks exist on Mars. Additionally, transient spikes in atmospheric methane have been observed. Methane can be produced by biological processes, but also by geological activity. Current evidence remains ambiguous, and definitive answers will require more time and investigation. Mars is no longer the world it once was, but that doesn't make it unreachable. Reaching Mars is difficult. Nearly half of all missions sent there have failed. Yet success is possible. Humanity has already achieved remarkable feats. Orbiters, landers, and rovers have revolutionized our understanding of the red planet. In just a few decades, we've learned more than in all previous centuries combined. So far, only robots have gone. But while efficient and cost-effective, they are slow and limited. Humans could accomplish in weeks what takes rovers years. Yet humans require air, water, food, and protection from radiation and vacuum. Still, sending humans to Mars no longer seems like science fiction. Rocket technology is advancing, and systems for crewed missions are under active development. Scientists are already evaluating potential landing sites and habitats. One promising idea involves using lava tubes, natural caves formed by ancient lava flows, where the surface cooled to form a roof while molten rock continued flowing beneath. Skylight openings, pits, have been observed from orbit, confirming their existence. These tubes could shield future colonists from radiation, extreme temperatures, and dust storms. Sealed and pressurized, they could serve as safe bases for exploring the planet and gathering knowledge far beyond what robots alone can achieve. We don't know exactly when humans will set foot on Mars, perhaps in a few decades, but it will happen. And eventually, people will live there. In summary, we now know that Mars is smaller and colder than Earth, with polar ice caps and rust-colored dust covering its surface. It hosts the solar system's tallest volcano and largest canyon. Though dry today, it was once warmer, wetter, and shrouded in a thicker atmosphere, and may even have harbored life.